We're going to prove in this video that the derivative of sine theta with respect to theta is cos theta. But we have to do this in two parts. Part two will be the direct proof of that. Part one, though, is going to be a proof that the limit as theta goes to 0 of sine theta over theta equals 1. Why are we proving that? We're proving that because it actually comes up in part two. And so what our strategy here is prove that first part, and then when it comes up in part two, the direct proof that the derivative of sine theta with respect to theta is cos theta, we'll be able to just sub in the result. Okay, so first thing we want to do is to understand that if we have a sector of a circle, that whatever the that sector is going to represent a fraction of the area of a circle as a whole. Now, the area of a circle as a whole is pi r squared. So the area of that, the fraction that that sector represents of the circle as a whole is going to be theta over 2 pi. Now, why is that true? Think of it this way. If that sector, if that theta in the middle, if that was equal to 60 degrees, we would have no problem thinking, okay, well, that means it's 1/6 of a circle. It's 60 degrees over 360 degrees of the area of a circle. It's 1/6 of the overall area. And if we wrote that down, most people would be okay with that. Well, that's what we're doing here. We're measuring theta in radians, and 2 pi is equal to 360 degrees. So whatever that measurement is in radians, theta over 2 pi times pi r squared, that will represent the area of that sector. And the pi's will cancel out here. And so if we're measuring theta in radians, we can say that the area of the sector is theta over 2 times r squared. So a little bit more of a description of that is shown on the bottom of your screen. But we come up with this statement, and this is the statement that we're going to go with from here. The area of that yellow sector is theta over 2 times r squared. Okay, now let's assume at this point that we're talking about a circle with a radius of 1. So theta over 2 times r squared is going to equal theta over 2 times 1 squared. In other words, just theta over 2. We're going to redraw the circle now. Okay, we'll draw a unit circle as we often do. And we're going to label some points. We've got the origin, and we've got point A, point B, D, and C, as you can see. Now, we're going to let that sector, OAB, be represented in gold. And we're going to let the triangle, OCB, be represented in green. And we're going to let the sector OCD be represented in blue. And so looking at that, you can see, well, the smallest gold sector is smaller than the triangle, and the triangle is smaller than the large blue sector. So obviously, we can make that statement just by observation. Okay, so now that we have that set down, just to really re-emphasize what we're saying, we're going to focus on that smallest sector. Now, the length of OB is the radius of that little circle from which sector OAB comes. So in other words, OB is just that little tiny piece. Now, we know that B and C have the same x-coordinate because they're equally far along on the x-axis. So they clearly have the same x-coordinate. Now, point C is on the outside. Point C right here, that's on the outside of a unit circle. Well, we know the x-coordinate on the outside of a unit circle has to be cos theta. And so we can say that the radius of the little circle from which that sector is coming from must be equal to cos theta. So this is the radius of the little circle from which that golden sector comes. The radius of that little circle is just equal to the x-coordinate of C, but since C is a point on the outside of a unit circle, its x-coordinate must be cos theta. Okay, so we can say that that x-coordinate is safely cos theta. Now, we know that the area of that sector, based on what we had agreed on earlier, that area of that golden sector must be theta over 2 times r squared. We know r, based on our conversation a minute ago, is cos theta. So the area of that gold sector is really theta over 2 cos squared theta. So up here, when we're talking about this area of sector OAB, we can now say theta over 2 cos squared theta. We can put a assign a value to it. Now let's look at the triangle here. Well, this is kind of interesting because we already know what the area of what the base of that triangle is. It's equal to cos theta, the x-coordinate of B, based on all our previous discussion. Well, what's the height of that triangle? Well, the height of that triangle is going to be equal to the y-coordinate of C, right here. The height of that triangle is equal to the y-coordinate of C. Now, since C is a point on the outside of a unit circle, the y-coordinate of C must be sine theta. So the area of that triangle, the green one that you're looking at, is obviously 1/2 base times height. So it's 1/2 cos theta sine theta. That's the area of the green triangle. Okay, so what we've just shown, since the area of sector OAB must be less than or equal to the area of sector O of triangle OCB, therefore theta over 2 times cos squared theta must be less than or equal to 1/2 cos theta sine theta. All right, interesting. Now we'll keep on going. What we now have here is a big blue sector. Now that big blue sector is a sector of the circle, the whole big circle, which we agreed a moment ago is a unit circle. So since the radius of that blue sector that we're looking at is 1, we can say that the area of the circle is theta over 2 times 1 squared, which is just theta over 2. And so now what we've summarized here are the areas of those 3 shapes that we're looking at. And since the area of sector OAB must be less than or equal to the area of triangle OCB must be less than or equal to the area of sector OCD, that means theta over 2 times cos squared theta must be less than or equal to 1 over 2 cos theta sine theta must be less than or equal to theta over 2. And that's what we've now written on our screen. Okay? So there it is, nicely worded up at the top left of your screen. Now, what we're going to do is we're going to multiply the left and the middle and the right each by 2 over theta cos theta. Now, as often happens in these proofs, someone else has already done the hard work of figuring out what's the convenient quantity to multiply everything by. So this 2 is going to cancel with that 2. This theta is going to cancel with this theta. And we've got a cos theta in the denominator and a cos squared theta in the numerator, so they'll cancel out. And what we'll be left with there is just a cos theta. Now, in the second quantity here, we have a 2 in the denominator and a 2 in the numerator. They'll cancel out. We have a cos theta in the numerator, cos theta in the denominator. They'll cancel out. And so that quantity will just be sine theta over theta. And then we have a theta over 2 times 2 over theta cos theta. These thetas will cancel. These 2's will cancel. And we'll just have 1 over cos theta as that third term. And so what we can then say, simplifying everything like we just showed, that we can say that cos theta is less than or equal to sine theta over theta, which is less than or equal to 1 over cos theta. Okay, so far so good. Now, putting that again nicely up in the top left, what we're now going to do is determine the limit as theta goes to 0 of the left, middle, and right. So the limit as theta goes to 0 of this quantity is less than or equal to the limit as theta goes to 0 of this quantity is less than or equal to the limit as theta goes to 0 of the quantity on the far right. Okay, and now we have it written that way. Now, we can directly sub in a theta value of 0 for theta right there, and we just get cos of 0. We can't directly sub in a theta value of 0 in that middle portion because it would give us a denominator of 0. So we're not going to do that. It would actually give us a numerator of 0 as well, and as you recall from your limits section, that's an indeterminate form. Now but we can directly sub in a theta value of 0 to this rightmost part. Sometimes students are a little caught off guard by that. They think that it's making the denominator 0. But remember, the cos of 0 is 1, so we can sub a 0 in. And ultimately what we get is that 1 is less than or equal to the limit as theta goes to 0 of sine theta over 0, which is less than or equal to 1 over 1, or in other words, 1. Now, look at what we've got here. We know that the limit as theta goes to 0 of sine theta over theta is greater than or equal to 1, based on that 1 on the left. But we also know that it's less than or equal to 1, based on that 1 on the right. The only way it's both greater than or equal to 1 and also less than or equal to 1 is if it is equal to 1. And some people call this the squeeze theorem. So like we say there, this next part's really cool. The only way that 1 can be less than or equal to and greater than or equal to a particular quantity is if the quantity is equal to 1. So that quantity is being squeezed, and therefore the limit as theta goes to 0 of sine theta over theta equals 1. And that's what's written at the bottom here. Now, you might be wondering, why did we figure that out? Well, it's going to come now. It's going to show up in the proof that we're about to do, which is the one that we are really interested in, which is this statement. We're going to prove that the derivative of sine theta with respect to theta is cos theta. So how do we do it? Well, let's start by just simply using the definition of a derivative. The derivative of sine theta with respect to theta is the limit as h goes to 0 of sine theta plus h minus sine theta over h. Now remember our compound angle formulas. The sine of theta plus h is sine theta cos h plus cos theta sine h. Okay? And what we can now do is reorder this a little bit. We've got sine theta cos h. We're just going to move this sine theta here, and we're going to move that other term to the end. No big deal there. And then, after we do that, we're just going to break this fraction apart. So we're going to have these first two terms over h, and then this last quantity over h. Okay? Now, at this point, we're going to factor each numerator. So what that means is we're going to common factor out the sine of theta from this first numerator. When we do that, we're left with cos of h minus 1. And we're going to factor the cos of theta out of this numerator. In other words, what we're going to do is we're going to say that the cos of theta times the sine of h over h is just equal to the cos of theta times the sine of h over h. Okay? And that gets us to this part right here. Okay? Now, what we're going to do is we're going to take this limit notation that we have in front of the whole thing, that limit notation right there, and we're actually going to place it once in front of sine theta times cos h minus 1 over h, and also once in front of cos theta times sine h over h. We're actually allowed to do that. And this is what we now have. Now, please note that this sine of theta right here is completely independent of h. So we can actually put that in front. And also, please note that this cos of theta, that's also completely independent of the h that we're taking the limit, the h in the bottom of the limit. So we can put that in front of the limit notation as well. And so that's what we've done in our next line. Okay? Now, at this point, you'll notice, okay, yeah, we just spent a whole bunch of time a while ago saying that the limit as theta goes to 0 of sine of theta over theta equals 1. So clearly, by extension, we can say the limit as h goes to 0 of the sine of h over h is equal to 1. So this circled quantity right there, that's equal to 1. We can do a quick substitution. And this quantity right here is something that we can deal with if we multiply both numerator and denominator by the cos of h plus 1. As it stands right now, this quantity would give us the indeterminate form, because if we substituted an h value of 0 directly in there, we would get the cos of 0 minus 1 over 0. We know the cos of 0 to be 1, so we'd get 1 minus 1 over 0. So that'd be 0 over 0. Well, we can't have that. That's the indeterminate form that we spent a lot of time on early in the course dealing with. So we have to have a method to get rid of that. And like it says at the bottom of your screen, that method will be to multiply top and bottom of that fraction by the cos of h plus 1. So that's what we do here. We multiply numerator and denominator by the cos of h plus 1. Notice that we've subbed in a 1 directly for that quantity there. Now, we're going to multiply those numerators and denominators. And when we do that, the cos of h times the cos of h is cos squared h. And then we add cos of h and subtract cos of h and subtract 1. So we get cos squared h minus 1. And then the denominators get multiplied just straightforwardly. We have h times cos of h plus 1. Now, cos of theta times 1 over here. Again, this 1 is what we spent a long time earlier determining. Obviously, that cos of theta times 1 is just cos of theta. So now we have the quantity shown at the bottom of your screen. Now, the cos squared h minus 1, we know that cos squared h plus sine squared h is equal to 1. So by extension, that means cos squared h is equal to 1 minus sine squared h. And that's what we've written here. So that means that the cos squared h minus 1, if I subtract 1 here, I also subtract 1 here. So cos squared h minus 1 would equal 1 minus sine squared h minus 1, or in other words, just negative sine squared h. So if my writing's gotten a little messy, just look at the top, the typed portion at the bottom. And that's what we're saying. So that circled quantity up in the formal part here, this circled quantity right there, this circled quantity right there, that's just the same as negative sine squared h. So we can sub that in now. Now, let's break apart that fraction that we're talking about. Okay, so leaving out, that's where we had left it off a moment ago. Well, we're going to call this fraction here negative sine of h over h times sine of h over cos of h plus 1. Because obviously, if we were given negative sine of h over h times the sine of h over cos of h plus 1, we would know that we can multiply numerators and multiply denominators. So all we're saying to you here is go backwards. Taking the result, break it up into the components. And now the next thing we're going to say is, instead of looking in this square bracket right here, instead of taking the limit of that product, let's take the product of the limits. Or another way of saying that is take that limit sign and just distribute it right in front of that second fraction. And that's what we're showing at the bottom. Now, that factor of negative 1 in front of the sine h, we can put that in front. because it's independent of h. So we can actually take that factor of -1, put it in front of the limit notation. There's nothing wrong with that. So that's what we do. And now notice one more time it comes up that this limit as h goes to 0 of the sine of h over h is equal to 1. We knew that. And now we've gotten ourselves to something that we can actually sub an h value of 0 straight into. So the first circled thing is equal to 1. We spent a long time discussing that at the start of this video. We have a negative there, so we'll keep it. We're not getting rid of that negative. And then we're going to multiply by the second limit. Well, the first rule of limits is if you work yourself down to where you can sub the value straight in, do it. And that's what we've done. We have the sine of 0 over the cos of 0 plus 1. Well, the sine of 0 is 0, and the cos of 0 is 1, so that's 1 plus 1. That's the same as 0 over 2, which is the same as 0. So this circled limit right here, it's just equal to 0, and there's nothing wrong with having a limit equal to 0. Okay? So that's what we're describing here. We're just going to sub in an h value of 0, and the first part of the proof established that that limit there is equal to 1. So we get everything we just described, this -1 times the sine of 0 over the cos of 0 plus 1, which is -1 times 0 over 2, which is -1 times 0. So what we have is the sine of theta times 0 plus the cos of theta, which is equal to cos of theta. Okay, so the sine of theta times -1 times 0 is the same as the sine of theta times 0. Anything times 0 is 0, so we have a 0, but we also have that cos theta that's been there all along. And so what we've just shown, believe it or not, is that the derivative of sine theta with respect to theta equals cos theta.